Let's continue with this example that we started with. So I started with this flow. I constructed the residual graph for this flow. And in the residual graph, I identified the path between S on this end and T on this end. So what I have to do now is I have to tell you how to use that path in order to augment the value of the flow. So the rule is the following. Whenever you took a forward edge, an edge that actually existed in the original graph, you're going to add to it the value of the... So first of all, you're going to pick on this path the smallest capacity. So in this case, it is going to be 4. That's the smallest capacity. And then let this capacity be, I don't know, A. Then add A to the flow value of the edges in the graph in the direction of the path, and subtract A from the value of the flow on edges in the reverse direction. So let's take a look. This is the original graph. We took this edge in its original direction. So we have to, first of all, the value of A is 4, right? Because 5, 4, and 5, the smallest one is 4. On this edge, we are in the same direction as in the original graph, so this 8 becomes 8 plus 4. On this edge, we are going in this direction, but the original direction of the graph is the reverse. So this becomes 4 minus 4. And on this edge, we are going in this direction, so this becomes 15 plus 4. So the new flow has the value of 9 here, value of 0 here, and value of 19 over here. So new flow so I'm going to have again so on this one we still have 11 over 16. On this one we have what is the value now on this one? What was it before? I'm sorry. What was this value before? It must have been 8 over 13, right? That's correct. So it would be 12 over 13. Here we still have 11 over 14. Here we still have 0 over 10. I think this was 1 over 4, right? Here we have 0 over 9 now. Here we have 12 over 12. Here we have, it used to be 15 over 20. So now it is 19 over 20. Here we have 7 over 7. and here we have 4 over 4. Is that correct? Or not? Okay, so this is now the new flow. So now we have to repeat the algorithm. Repeat means we have to find the residual graph for this flow. So let's do it together. Let's find the residual graph for this new flow. Okay, so we have a forward edge. What's the capacity of the forward edge? 5. Capacity of the backward edge is 11. Here the capacity of the forward edge is 1. That of the backward edge is 12. Same way here, the capacity of the forward edge is 11. Backward edge is 3. Here we have, in this direction, 9. Here we have 3, backward 11. Here we only have backward 12. Here we have forward 1, backward 0. Backward 19. Here we have only in this direction 4. And then we have in this direction 7. Is that correct? Can you check? Yes.
I think that the first two, one would be a lot of 3.
Here?
Exactly the
Okay, so we would have to put something over here with value 10, right? And something in the direction, in this direction, with a value of 3, and in this, in this direction with a value of 3, and in this direction with a value of, no, this is correct. So this is, yeah, this is exactly the other. So that's what you're saying. The 11 should be 3 and 3 should be 11. Is that what you're saying? And I think you're right. Okay. Okay, so this is the residual graph after slight errors. And now the question is, can we find a path from here to here? Still, so 9 should be the other direction. Okay, so we have a 0 in this direction, so we have to reverse it. This one?
Yeah.
Okay.
10 at what?
So this guy becomes a 10 but in the other direction, and this guy becomes a 3 in this direction. Is that what you're saying? So 13, and then coming back would be 1. Okay. Not that it changes much, but what did we do here? Is that the same thing here? I can't read it. Can you read it in your script?
In the script, the 9 is in the opposite direction.
9 is in the opposite direction. Okay, so here this is correct so far, right? Okay. So, you know, whenever you have the flow value of 0, you can definitely augment that flow value. So it has to go in this direction, but you cannot take anything off. So you cannot go in the other direction. That's correct. This has to be this way. So let's go back to the definitions. You see, whenever the value of the flow is less than the capacity, you keep the arrow. And if the value of the flow is larger than 0, you're going to add the inverse of the arrow. And here the value of the flow is 0, so you keep the arrow and then the other one. Whereas when you are right at capacity, you have to inverse the direction of the edge. Okay, now coming back to this guy. That's okay? All right. So let's see whether we can we find a path from S to T in this graph? Yes, which one is it? What is the path from S to T? There is none. Why? Because, okay, if you end up in this node, you can still go forward. But if you end up in this node, you cannot go forward. If you end up in this node, you cannot go forward. And there is no connection between this and this, so there is no path from S to T. In this residual graph. And this is the end of the algorithm. At least, it's certainly the end of the algorithm, but it's not clear that this has given you the right solution. But certainly the algorithm stops at this point. Now, why is this the right solution? The thing is, so therefore, algorithm stops. So in order to show that this is the correct solution, we have to use this combinatorial approach with the cuts in the graph. So we are going to look at all the nodes in the residual graph that are reachable from S. What are the nodes that are reachable from S? There is S itself. This guy is reachable. This guy is reachable. And this guy is reachable. All the other nodes are not reachable. So what does it mean to be not reachable? It means that the edges that we picked that go from out of this green set either are right at their capacity or 0. That's why they're going in weird, in directions that we can't really use. Now, if you look at the corresponding nodes over here, you will see that any edge that goes from the green set to the red set, so all the sets that go from green to red, for those edges, what can we say about the value of the flow on edges that go from green to red? What are they? They're full, they're equal to the capacity. What can we say about the value of the edges coming from red into the green set? They're 0. So in this case, if we see that for all E in E of ST, the value of the flow is equal to the capacity, and for all E in TS, the value of the flow is 0. And so by this lemma, by this corollary that we proved, the value of the flow is maximal, because for this particular cut, it attains the upper bound in the corollary. So therefore, this is the maximal flow. This is the proof that this is the maximal flow. So that means that the value of the flow is equal to all E in ST C of E, and therefore it's a maximal flow. So here is the proof that in this particular case, the flow that you found has its maximal value. You cannot augment this flow any further. But this is much more general, in the sense that whenever the fourth Fulkerson algorithm stops, what you get, the nodes that are reachable in the residual graph form, and the nodes that are not reachable form a cut. And for this cut, the value of the flow on all the forward edges is equal to the capacity, and all the backward edges, it has to be equal to 0. The reason is, if there was a backward edge, with a value of a flow not equal to 0, you would have to reverse that edge in the residual graph, and you would get a connection from S to T. The same way, if there is an edge that goes from S to T and doesn't have, where the flow value is not the capacity, in the residual graph, that edge would exist, and you could go from S to T. So here is the theorem that goes with it. And so I just showed to you this theorem in a very particular case. The theorem says that if you have a flow in such a network, then the following are equivalent. You have a maximal flow, and the residual graph does not have an f-augmenting path. And the value of the flow, there exists a cut such that the value of the flow is equal to the sum of the capacities of all the forward flowing edges. This is a theorem. You just saw an instantiation of this theorem in this example. And so I will give you, before going through the formal proof, I will give you an argument why. If the flow is maximal, then there cannot be an f-augmenting path. It's clear. Because if there was an f-augmenting path, you could augment the value of this flow. That's why the name is, it's an augmenting path. So therefore, if the flow is maximal, there is no augmenting path. If there is no augmenting path, then there exists a cut with this condition. The reason is, if you take all the nodes that are reachable from S in the residual graph, you take all the nodes that are reachable, then these nodes, there is no, for all the edges that go from these reachable nodes to non-reachable nodes, you have to be right at the capacity. And for all the edges that go from non-reachable nodes to reachable nodes, you have to have value 0, because otherwise in the residual graph you would have an arrow in the wrong direction. This is essentially, that's all that, and the fact that C implies A was the corollary. So let's look at the proof. So as I said, A to B, if you have a maximal flow, you cannot have an augmenting path. Why? Because suppose that you had an augmenting path, and gamma is the minimum capacity on this augmenting path in the residual graph. Then you can always increase by gamma the value of the flow. And the reason that you can actually increase it is you're increasing the value of the flow, but what I didn't show you is that what you get afterwards is still a flow. Meaning that for every node, the sum of whatever is incoming is equal to the sum of whatever is outgoing out of that flow. But that is clear from the algorithm, because what you do is on all the forward edges you add the value of the flow, and on the backward edges coming into this you are subtracting that flow. So altogether it's a zero sum for the inner nodes of the edges. So if the flow is maximal, obviously there cannot be an augmenting path. So suppose that this GF does not contain augmenting paths. And then what you do is you're going to call the set S all the nodes that are reachable from S in this residual graph, and T all the nodes that are not reachable. And certainly S itself is reachable, so little s is an element of capital S. T is not reachable because there is no path in this residual graph, so T is not an element S. So this is a cut. But then what do we know? What do we know? We know that for every forward flowing edge, because there is no, because we don't have an edge that goes from S to T in the residual graph, the value of the flow on all forward flowing edges has to be equal to the capacity, because if it was smaller than the capacity, we would still have that edge. And for all the backward flowing edges, the value of the flow has to be 0, because if it wasn't 0, we would have to reverse that edge, which would give us something from S to something from T, which doesn't exist. So it has to be 0. And therefore, the value of the flow is this thing. And by this lemma, we get the equivalence. It's a very nice theorem and very nice, very powerful algorithm. So, you know, there is an interesting thing to note here. The only reason we could actually get to this algorithm is through this combinatorial approach. We had to get a combinatorial description of these optimal flows using the cuts in a graph. You know, originally these flows had nothing to do with cuts in the graph, but for some odd reason the cuts are incredibly important for this algorithm. And if you think about the notion of a cut, that is really how you get this algorithm. And if one of you ever takes the advanced algorithms class with me, which I'm not sure I will teach in the next few years, but there I will tell you what the real reason behind this algorithm is. So that's a type of algorithm that's called the primal dual approximation scheme that for problems like this leads to an exact solution, and for some other problems that are very hard to solve leads to an approximate solution. So this whole setup here is this is a prime example of a very large variety of algorithms that unfortunately I can't give you in this elementary class. They're much more complicated. Okay, so here is the Ford-Fulkerson algorithm. So somebody, you asked me, how do you start the algorithm? What flow do you take for the start? Well, you can take the zero flow. The algorithm, the flow that assigns to every edge the value 0 is a flow, obviously. You know, it's the trivial flow. But you start with that trivial flow, and then you continue building residual graphs and finding f-augmenting paths as you go along until the algorithm stops. So that's the algorithm. Now the question is, how many times do you have to do it before the algorithm stops? Here is a bad example. It depends on how you choose your augmenting path. The bad example is this one. So here is a graph. You have capacities of 1,000,000 on these edges and a capacity of 1 on this edge. So obviously, so what is the value, the best flow you can find in this graph? What value does it have? From S to T. What's the best flow from S to T in this graph? 2 million. You put the full capacity here, full capacity here, full capacity here, and full capacity here. That gives you 2 million as the best value of the flow. So let's try to apply the Ford-Fulkerson algorithm. So we start with the zero flow. When you start with the zero flow, the residual graph is equal to the original graph. So you start with that, and you know, instead of taking this augmenting path, you may take this augmenting path. And then the minimum value that you find is 1. And this is by how much you're going to improve your value of your flow, by 1. So in the next round, you have a flow of value 1. And then you're going to create again the residual graph. Here, these edges become, you know, 10 to the 1 million minus 1, and then you have an edge backward here. This one goes over here. And you may, for example, find this path as your augmenting path, increasing the value of your flow again by 1 only. So if you sort of do this stupid choice over and over again, you will need 2 million rounds of this algorithm in order to get to the full value. And if this wasn't 1 million, but you know, a gazillion, then you would do a 2 gazillion thing. So you see, the way you choose the augmenting path in the graph is extremely important. Is absolutely important. So people have shown, one of those people is Dick Karp, but I don't know with whom together. They have shown us that if you find the augmenting path using a breadth-first search, so here there is really a difference between depth-first and breadth-first search. If you do a breadth-first search for the augmenting path, then you will get an algorithm that that every time you will find it in time O of m, where m is the number of edges, and altogether you will have a polynomial time algorithm. Otherwise, the algorithm is not necessarily polynomial time. If you find the augmenting path in the wrong way, then your algorithm may just be, very, very inefficient. But if you do it with a breadth-first search, you're going to be okay. All right. So here again, an example, just for the fun of it. So we start with a graph that has these numbers as its capacity. And let's say I have the following flow on this graph already found. So it puts a 1 here, a 1 here, and a 1 here. And then I find the residual graph. And in the residual graph, so in this residual graph, this has capacity 0. These guys will keep their direction. This guy becomes 2 arrows. This guy becomes 2 arrows. This becomes 2 arrows, etc., etc. And eventually you find this graph over here. You find an augmenting path over here with a value of 1. Sorry, with the value of 4. And you're going to continue. Sorry, what is the value here? So 7, that's right, a value of 3, because the capacity on the forward edge here is 3. So you can augment the value of the flow by 3. And then you again go to the residual graph over here. And maybe you can find, you augment the value of your flow by 2. And so on, and so on, and so on. And eventually you will get to these values. So you will have a flow of value 8 at the end, and everything that's reachable from the node in the residual graph, these are this node and this node, gives you something that's called a minimum cut. So that is a minimum cut, is a cut for which the value of the flow along the forward edges is always the capacity, and along the backward edges is always 0. Okay. So this is something you should really practice. And I think on the exercise sheets we have something, right, this week, or is it next week? I don't remember. This week, yeah, next week. Okay. So let me give you an example of this, an application. I mean, the algorithm is widely applicable, but let me give you one possible application. It's called the maximum bipartite matching problem. So here's the example. Let's say you have a dormitory like EPFL has, and you have students, and you want to assign rooms, dormitory rooms, to students. Now we are not at EPFL, so we are at the university where students actually can give choices for their rooms in dormitories. I don't think at EPFL you can give choices. You just take whatever you get, if you get something. So maybe each student is going to give a choice of the rooms. Maybe this room is the least desirable because it's next to the laundry room and whatever, maybe. And there are some rooms that are desirable, like these two, and so on. So here you have the students, and they have given choices for their rooms. And now you want to have what we call a maximum bipartite matching. So you want to find the maximum subset of the students such that they can get rooms of their choice on the right-hand side. So here is the problem. So we want to find a subset. So you have a bipartite graph with m nodes on the left, n nodes on the right, and a matching of size L is the following. You choose L nodes on the left, L nodes on the right, and then every node on the left is connected to exactly one node on the right. That's what the matching is. Is that clear? So you want to choose, so this is for the student problem, you want to match every student with exactly one room. So no room should have two students, no student should have two rooms in this setting. So how do we find a solution to the maximum bipartite matching problem? So let me write it down for you again. So we have a bipartite graph between m nodes on the left and n nodes on the right. A matching of size L is a collection of L edges of the graph for which the endpoints are disjoint. The sets of the endpoints are disjoint. So let's see, let's take a look. So maybe we look at this graph. So can you give me a matching of size 1? What's a matching of size 1? Just an edge. An edge is a matching of size 1. So that's clear. Can you give me a matching of size 2? So let me write down the names here. 1, 2, 3, 4. A, B, C, D, and E. Can you give me a matching of size 2? So these are the matchings. So for example, here is a matching of size 1. There is only one edge. Can you give me a matching of size 2? That is two edges that have disjoint endpoints. So two edges for which the endpoints are different. Anyone? Is that clear? Maybe it's not clear.
1A, 4B.
Sorry?
1A, 4B.
1A and 4B, thank you. So 1A and 4B. You see that the endpoints are different. These are edges. There is an edge from 1 to A, from 4 to B, and the endpoints are different. Can you give me a matching of size 3? Okay, 1A, 4B, and then 2D, for example. That's a matching of size 3. What about the matching of size 4? Three? Okay, good, very good. So that's a matching of size 4. Is there a matching of size 5? Impossible, absolutely impossible, because if you had a matching of size 5, the left endpoint in two of these, there would be two edges with the same endpoint on the left-hand side, because there are only 4 points on the left. So impossible. So this is, for example, a maximal matching. So the question is, given such a bipartite graph, find the maximal matching in this bipartite graph. In a given bipartite graph. So I told you, for example, an application would be matching students to dormitory rooms, for example. Or whenever you have demands and you have people and you have services and you want to match these people to those services, you can always do that. Processor, processes and processors. So you have processes that are waiting to be processed, but they can only be processed on processors of a certain strength. And so you want to find a matching. At any point in time, you want to find, you want to assign tasks to the processors according to the processes that are there. So for example, if you have a network, so that's one of the things we always do when we do calculations, large-scale calculations. We tell, for example, this processor, this process needs a 64-bit processor, or this process needs, a machine with at least 4 gigabytes of RAM, or this kind of stuff. So this way you can match processes to processors. So how do we do this? It's not completely clear, but with the Ford-Fulkerson algorithm, it's a breeze. Very simple. What you do is the following. You take the left nodes, you take the right nodes, you create an artificial node S on the left, you create an artificial node T on the right. You're going to create directions for the edges from left to right. And all the edges in the original graph, so you're going to connect S to all the left edges, and you're going to connect all the right edges to T. And all the edges will have capacity 1. So this is the network you create from your original problem. And then you're going to use the Ford-Fulkerson algorithm to find a maximum flow from S to T. What happens to this maximum flow once you have it? The point is, the way the Ford-Fulkerson algorithm works, the maximum flow will have integer values because of the Ford-Fulkerson algorithm. Right? The maximum flow will have integer values because at any point in time, you're going to add the value of an augmenting path to the value of the flow. And this value of the augmenting path is 1 or 0. So the value of the flow will be 1 or, the flow values on the edges will be 1 or 0 if you apply the Ford-Fulkerson algorithm. Moreover, because of the conservation of flow, the flow that is coming into every node has to be equal to the flow that is outgoing. So this means for every one of these nodes, you have to choose exactly one edge, or at most one edge. Because the flow that comes to every node will be at most 1, so you have to choose for every node at most one edge that goes out, no more. The same way, for every node that is incoming here, there must be at most one edge that has a flow value of 1 that is connected to that node. Okay? So this means that when you have a flow on this network is a selection of the edges in such a way that the edges are disjoint. They have disjoint endpoints. Because if they had the same endpoint, then the flow outgoing from that node would be 2, but what is coming into the node is at most 1. It cannot work. The same way, if you chose 2 edges with that endpoint, then the incoming flow would be 2, but the outgoing flow would be 1, which is not possible. So for every node in this graph, every node on the left-hand side, you're going to select at most 1 outgoing edge, and for every node on the right-hand side, you're going to select at most 1 incoming edge. And the flow itself will therefore be a matching. Right? The flow will designate certain of these edges as with value 1 and all the others with value 0. Those that have a value 1 will be the edges in your matching. And this will be a matching because an edge that you have designated cannot have this, 2 edges cannot have the same endpoint because of the conservation of flow. And the value of the flow is therefore exactly the number of edges that you have picked. Because for every flow, the value on that edge is 1. So the value is exactly the number. So a flow is exactly a matching, and its value is exactly the number of edges in that matching. Therefore, the maximum flow on this graph, using the Ford-Fulkerson algorithm, is a maximum bipartite matching. It's exactly the same thing. It's important to note that this is because of the Ford-Fulkerson algorithm. I could design a flow here that would not have integer values. For example, I could have a flow, the 1 flows here, and 1/2 flows out here, and 1/2 flows out here. It's still a good flow, but it's not a flow that is generated by the Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm will give you a flow that has zeros and ones as its values because of the way it works. Because every time in an augmenting path, you're going to add the capacity of, the smallest capacity on the path to the value of the flow. And these capacities can only be zeros or ones. So here is the way you can do this. Eventually you will find this matching here with this algorithm. So here you have actually been able to satisfy all 4 students. So this is an example of the Ford-Fulkerson algorithm for finding the maximal bipartite matching. Yes?
Is it possible to modify this algorithm to put preferences, for example?
Okay. So the question that is being asked is, if we had weights on the edges? Priorities. So the question is, if this was not 1, but you would have put weights on the edges. So let's say this student would have said, well, this is the least preferable, I want to give it a 0.2, but I want to give this guy a 0.8, for example. Right? And then what you would like to do is you would like to find a set of edges such that the sum of their weights is maximized. That's what you want. You could do that too, yes. Okay, so there the value of the edge would be, the capacity would not be 1, would be its weight. And the cuts that you would get would be most probably those that, those students that are satisfied would be part of the cut. The ones that are not satisfied would be on the other side of the cut. Okay, so that's it for today with the Ford-Fulkerson algorithm. This is really a very interesting algorithm. It is very far-reaching and easy enough to explain, in a 3rd semester course within 1.5 hours. So next time we are going to talk about spanning trees. Thank you.